What's up guys, welcome back to the channel. In today's video I'm going to be going over the different memory segments in a program, and of course in this video I'm not going to go 100% in depth into everything, but I'm going to give a quick overview of what happens when your program's loaded and where all the data is stored. And I'm going to do that with a quick little diagram that I've created. So we start with our program, our executable file, and within this file there's a couple of different sections. And if you've ever done any assembly, you might be familiar with some of these sections that you declare in the assembly code before you assemble it. But the first section is the text section, and this is the section that contains all the code. So all your functions, any functions you write, for example, if you're thinking of a C program, any functions you write, this is where all the code for that goes, in the code section. Next is the initialized data. So if you've used NASM or another assembler to write assembly, this is the .data section, and this is where all the pre-initialized data goes. So from a C perspective, it's basically any global variables that you have, or static variables in C that you have, that come pre-initialized with some constant value. And after that is uninitialized data. So this is data that's just reserved. So for example, if you declare a global variable but you don't assign any values to it, this is where that uninitialized data is. And these are just basically bytes or sections of reserved bytes that are just for that data. And it's not pre-initialized with any value. So you can see by this bracket that I've added here signifies that these three sections are they're contained within your program executable file. But when you run a program, your OS will load this file into RAM. So this right here is our RAM, high address up here, low address up here, and I'll load these sections in. By the way, just a quick side note, this uninitialized data section, for those of you who've done assembly, this is the BSS section. But going back to the whole RAM model, this is our RAM, high address, low address. And when you run your program, the OS loads this into the RAM. And then after that, what it does is it creates a heap and a stack. So let's say this is remaining RAM allocated by the OS to our process. In the high address space, the OS will create a stack. And the reason it's created in the high address space is because the stack grows downwards. So every time a new function frame is added to the stack, it grows down and down and down. And the heap grows upwards because when we access bytes, when we go further into the bytes that we're accessing, we access higher addresses because we're adding to our pointers. So the heap goes up and up and up when when more is allocated to that heap. So once you need more memory, if the OS wants to allocate more to the heap, it'll grow up. So OS will allocate you a heap for your process and a stack for your process. And this whole block makes up the virtual address space for your process. So each process has its own virtual address space. And if you're thinking about RAM, let's say you have 16 GB of RAM. There's going to be 16 gigabytes of addressable space in that RAM. And those 16 gigabytes are going to be addressed via physical addresses. Now when you actually launch a process, the OS will create a virtual address space for your process. And when you access some sort of virtual address in this process, like let's say I dereference some pointer I've allocated in the heap, that virtual address is going to be translated to some physical address in some physical RAM. Which is why if I had two different processes, these processes are running in two different address spaces. So even if they access the same address virtually, if they dereference the same virtual address, they'll be dereferencing two different physical memory locations in RAM. So that's just a quick side note. Every process's virtual address space is separate from another process's address space. So dereferencing the same pointer in two different processes will not give you the same physical memory location. And then another thing I wanted to add was just a quick overview of the stack frame. So if you've watched my buffer overflows video, you might have seen this diagram I've used before. Inside the stack is going to be filled with many different function frames. So assuming like this is a C program, there'll be, or not even any program, there should be a standard for how your function frames are created. But especially in a C program, there'll be that standard, the ABI, so Application Binary Interface. There's a standard for how your function frames are managed, and especially how functions are called and all that. So inside the stack, there's many different frames, and I'll just pull out one frame here. So high address, low address, same sort of direction. Inside the frame, so on your highest address in the frame, there's going to be argument data. So I like to think of the argument data as actually part of the previous functions frame. So this argument data is what the previous function has pushed or has put on the stack for the function that it's about to call. So imagine that there's a previous function. So let's say there's another frame right above this one. The function of that frame has pushed this argument data onto the stack and then has called this function, which has created a new frame for itself. So this function, first when you call a function, the return address is pushed to the stack, and the return address is just the pointer to the memory of where the function should return to. So it's going to be a pointer to somewhere within this text section. And then we have saved registers. If you've done assembly, you know that there are different CPU registers where data is stored, and you can save them. For example, if the standard doesn't allow you to use those registers or if the standard doesn't allow you to destroy the value in those registers and you still want to use them, you have to save them so that when you return from the frame, those register values still exist for the previous function. And after that, the compiler, let's say if you're writing in C again, the compiler will create basically a frame for or a little section for local variables, and that will be the lowest point in your stack frame. So that's it for the quick overview of the memory layout. Hope you guys enjoyed the video, and I'll see you in the next one.